Alright, so for section 5.2, 5.2 is essentially just an extension of 5.1. In 5.1, we see that if we want to estimate the area underneath a curve, we can do that by just putting in some rectangle underneath that curve and then try to find the area of the rectangles. We also see that as we put in more and more rectangles, the area become more and more precise. And 5.2 simply extend that notion of putting in infinitely arbitrarily many rectangles underneath a curve and give it a name. So let xi star be a value in xi minus 1, xi. Call xi star the sample point. Let f be a function defined on AB. We divide AB into n subinterval of equal width. We call that delta x just as before, nothing has changed. Then the definite integral, this is the new thing. We call the definite integral of f is going to be represented by this equation on the left right there. We say the integral of f from a to b, that is going to be defined as the limit of the sum of f of xi star times delta x as n go to infinity. We call this sum the Riemann sum. I mean, provided the limit exists, of course. And if it does, we say that f is integrable on a to b. So this is just a definition. This on the left is simply just a shorter way to say everything that's on the right, just as we did with derivative. Instead of saying the limit as h go to 0 of some quotient function, we say the derivative. Instead of saying limit of the sum of some rectangles, some amount of rectangles, we say the integral. Now note that the xi before were just any sample value. If we were to actually try to make this the same as 5.1, we have to choose our xi to be the endpoints that we found in 5.1. And indeed, this theorem say that if f is integrable on a to b, then it doesn't matter what point you choose as your sample point. It can be the left endpoint, it can be the right endpoint, or it can be any point in between. The limit as n go to infinity of the sum is going to be exactly the same. So let's take a look at an example. Let's try to rewrite a sum into an integral. In this example, we want to express the limit of this sum xi cubed plus xi times sine of xi times delta x as an integral on 0 to pi. Let's remind ourselves what it means to be an integral. An integral from a to b of f of x dx is equal to the limit as n go to infinity, the sum of I equal to 1 to n, f of xi, delta x. So essentially what we want to do here is we want to take a look at the right hand side, match up the values, and then use that to plug in everything on the left hand side. Well, we already know a and b. They tell us a and b. A is 0, b is pi. Inside here, that is indeed the f of x. So the f of x is actually equal to x cubed. Wherever you see an xi, just replace it with an x, plus x sine of x. So we'll put everything together and the integral is going to be from 0 to pi of x cubed plus x sine of x, cannot forget that dx, And that's the solution. Rewriting a sum as an integral. In this part, let me talk a little bit more about summation. Let's take a look at the first summation. Let's suppose we want to add all value 1 plus 2 plus 3 plus all the way up to some fixed value n. What is the answer? I'm going to first rewrite this as a sum by saying we start from 1, we just add up the term, and we stop when we get to n. And indeed, the sum for this is going to be equal to n times n plus 1 divided by 2. Whenever you are adding up consecutive integer, instead of adding up all the number and plugging all of that into your calculator, all you need is to know where you stop and plug in the right hand side. For example, I want to add values from 1 to 2 to 3 all the way up to 100. From the previous formula, instead of putting all of this into my calculator, I can just put in 100 times 101 divided by 2. And so the sum of everything on the left hand side is just 50 times 101, which is just going to be 5050. And there's also a formula for square, for cube, and so on and so forth. I'll just give it right here. If you want to add up all consecutive squares, that's actually going to be equal to n plus 1, 2n plus 1 divided by 6. For cube, which we never really use but might happen, it's going to be n plus 1 all over 2 and squares. If you are taking the sum over some constant, well, that just means you are adding up this constant n time. So if you are summing up a constant, the result will just be n times the constant itself. And another property that is going to be very helpful is that for sum, if it's a finite sum, we can actually split it up over addition and subtraction. What I mean is that the sum of AI plus BI is going to be equal to the sum of AI plus the sum of BI. And the same is going to go for subtraction. It's going to be the sum of AI minus the sum of BI. More on this, all of these formulas can be found inside the notes.